It all started with a simple idea. What if we built a big box in the pasture that opens up to the universe? I knew I had to be strategic. You don't just drop observatory into conversation unless you're holding a bouquet or an offering to clean the shop first. So I said, what if we put something out by the pond? Nothing big, just astronomy big. She gave me the look. You know the one. The look that says, are you building another thing that requires a permit, batteries, or a 3-day trenching project? I said, no, this is different. This one's solar powered, off grid. It's like camping with science. The roof slides open, I added, like a garage door for stars. It'll be made of cedar. There are windows. It smells nice. And somehow, after a few days of careful negotiation and possible offering to be on dish duty until further notice, she said the words every stargazer dreams of, as long as it doesn't block the view of the pond. And now here it stands, the fully solar-powered roll-off roof observatory, right here on the edge of the pond, a handcrafted portal to the cosmos, with just enough windows to look classy and just enough roof to dramatically disappear on cue. She got her beautiful view of the pond. I got a telescope cave with a disappearing ceiling. We both won. Before we get into the details of this observatory build, I want to be upfront. My background is in information technology, not construction. I spent 30 years in IT before retiring, and when my wife made it clear she didn't want me just sitting around the house, we bought a pretty rundown old home to renovate. That rebuild taught me a lot. How to frame, how to wire, how to troubleshoot problems I'd never encountered before. Everything you see in this video comes from that journey of learning by doing. Now that also means some of what I built could be completely wrong. I'm not a contractor, so if you're planning to build your own observatory, I strongly recommend watching a lot of videos, reading up on framing, electrical safety, and building codes. Do your homework and make sure your build is safe for you and for anyone else who is around it. With that said, here's how I built my off-grid roll-off roof observatory from the ground up. Hello fellow stargazers, my name is Zach and I'm going to show you my new off-grid observatory that I recently completed. One thing about this video is if I'm covering things that you're not interested in, check the timeline because I do have chapters. So if I'm covering a construction side of things that you don't care about, you want to know more about the solar, hover on a timeline and you'll be able to find this section that just talks about solar only. When I was researching for this design, I found quite a few builds that I really liked, and I incorporated some of those ideas into this design. One build I really like, and it's a pretty recent video, is Pat Cosgrove's Whispering Skies Observatory. He did a phenomenal job. He did an excellent job documenting the entire process, and I will link it below because it's a must-see video, especially if you're looking at building your own observatory. So with that, just how this video is going to flow is I'm going to talk about the different design aspects of it. We'll start with the outside construction, kind of from the ground up. We'll cover the solar, how the solar works, how it's powering the various devices, what you can expect out of a system this large. Actually, a system this small, I should say. This is not a large system by any means. We'll go inside, we'll look at the electronics on how things are automated, and we'll look at the equipment that I have. The observatory sits on 4 concrete piers, one at each corner, reinforced with rebar, and 2 wood midspan piers for additional support. These midspan piers were already in place as part of my original telescope deck build, so I chose to keep them. Each pier extends 36 inches below the ground level, reaching well below the frost line to ensure long-term stability. The reason I use concrete piers instead of a concrete slab is that this particular pasture is on a slope, and there's a significant water runoff during heavy rains. I knew the excess water would cause some ground stabilization issues in the future. Starting at the bottom, just on top of the piers, is the rim joist. This is what actually supports the building. Those are all double 2x8s. That is more than adequate to support the entire weight of this building. I think it's 1.5 or almost 2 times the support that's required. Of course, going across the support deck, as far as those joists, those are all 2x6s set at 24 on center. They support a 3/4 inch plywood deck that we walk on inside there. On these ends, well, you see these beams coming out where the actual roof rolls onto. There's actually double 2x8 vertical beams that support these 2x6s that are coming into or 2x8s that are coming into the building. Wanted to make sure we had plenty of support on these corners because you never want the roof to potentially have any kind of play or anything that may not possibly support it correctly. This roof is probably around 500 or 600 pounds. So, it's overkill for the amount of wood I use, but I wanted to make sure this thing was built like a tank and I would never have any problems with it. As far as the walls go on the inside, these are all 2x4s at 16 on center. There's 1/2-inch sheathing on both the inside and the outside. There's a house wrap that helps prevent against the elements. And then on top of that house wrap, we installed furring strips vertically so that the cedar boards would actually have something to attach to keep some separation from it. All the construction blogs I read said that is the only way to do it, to make sure that you don't get any type of potential rot from water or anything being held between the boards directly up close to the building. So if any water does get behind the cedar boards, it just runs down the house wrap and just drains out the bottom. I should also mention that the cedar siding was sourced locally from a small lumber yard, and I will say it is a much higher quality than anything you would find at the big box stores. This is rough cut cedar, so that means if you're buying a 1x8 by 8, you're truly getting a 1-inch by 8-inch by 8-foot board. Also, the local lumber yard I bought from gave me quite a few 10-foot boards mixed in with the 8-foot boards. Home Depot wanted $25 per board versus $7 per board from my local supplier. That gave me an immediate savings of $1,200 on this build. When I designed my roll-off roof observatory, I wanted it to feel like a natural part of the pasture, something that blended in visually rather than standing out. That led me to the tilt roof design. Slanted at 14 degrees, which gives me a simple, cabin-like look, while also aiding water runoff and keeping the structure a low profile. The 3 rectangular windows along the high side of the roof are purely aesthetic, added to enhance that primitive cabin feel. I found that the light they let in during the day interferes with the capture and calibration frames, so I plan to install some light blocking solution to resolve that in the future. The design as a whole is about finding the right balance, a structure that looks at home in its setting while supporting the demands of its purpose. The roof trusses were installed at 24 on center, and additional bracing was installed to prevent racking when the roof was opened. There are stop blocks installed at the end of the roll-off tracks to prevent the roof from falling off the end and causing a very bad day. I also installed a radiant barrier on the underside of the roof decking to help slow the heat that will radiate in the summer months. Actual roll-off mechanism of this roof, it rides on these V-tracks. So if you've ever seen these metal tracks that these cantilever security fences ride on, like when a car is pulling up and the whole gate slides sideways and there's that metal track on the ground, that's actually what is at the top of these walls that the roof actually rides on. The roof is held down with these large clamps. That keeps the roof from blowing away in the event of a high wind or a storm or anything like that. I'm gonna be over here doing these other ones. So, and we have these cane bolts on here too. There's actually another set on the outside. Once the roof is rolled out, I latch these on the outside. That keeps the roof from potentially sliding back when the telescopes are looking above the walls. We don't want the roof to slide back and actually hit those if there's like a really strong wind gust. So these cane bolts on the outside, they latch once the roof is completely slid open. So I'm gonna go ahead and slide this open. It's despite it being at least 500 pounds roof, it's not difficult to open. Just get a little momentum going and it'll slide right open. At some point in the future, I'll probably add a electric motor to it. But right now, this gives me the reason to come down here, anytime I want to do an observation. I don't want to get, lazy and, just do everything from the house, push a button and everything opens up. It's kind of fun just to come down here and see all your stuff and make sure a bird didn't, come in and decide to build a nest. So, go ahead and raise this up so you can see what the tracks look like up here. And as you can see, this is the V-track I was talking about. The wheels that the roof ride on in this V-track, there's 8 total. There's 4 on each side, and each wheel can support up to 450 pounds. So again, we're overkill on the actual design of it, but I never want to, have a mistake based on me cheaping out on something as critical as that. But it rides really smoothly on this track. Haven't had any issues at all with those particular wheels. I know garage rollers are popular in some roll-off roof setups, but I just chose to go this route. I feel like it was a better design for my particular build. And then this is the inside sheathing and stuff. It's all painted blue, nice dark color, so at nighttime you don't have reflective surfaces pushing back potentially into the objective of the telescope. This is a solar array that charges the batteries, that provides the power to all the equipment inside. Each panel is 100 watts, so 400 watts of power charging these batteries. I actually got these panels on Facebook Marketplace. Somebody had bought them, and either they couldn't use them for their project or something. I'm not sure what the deal was, but either way, $100 for 400 watts of power. You can't beat that deal. And that's a lot of things that I tried to buy for this project were either used or significantly discounted. You know, anywhere that you can save money on a project like this, you're for the better, especially if you can easily use that money for more scope technology. So we do have an extra panel, 2 panels, these little small ones. These power the 2 cameras that are out here. While the cameras don't use a lot of power themselves, anytime you can save a little bit of power consumption, you want to do that, especially in off-grids, because every little watt counts. So cameras are completely self-sustained with their own power solar panels, while everything else is basically using the batteries that these solar panels are charging. The charge controller that I'm using to take the power from the solar panels and put it into the batteries is a Victron MPPT 130. That's a 100 volt, 30 amp charge controller. The little device out to the right of it here is a battery protector. In the event that we were running low on power, it would actually detect that, and it would shut down power inside to protect these batteries from getting too discharged, you know, that could potentially damage them. Now, I will say that these are lithium iron phosphate batteries, so they do not suffer the same type of damage that a lead acid battery would experience if you did a full discharge or even a half discharge on them. Lead acids have to maintain a certain level, otherwise you can actually damage the cells. With your LiFePO 4 batteries, lithium iron batteries, they actually have a full discharge cycle that the manufacturer provided specs on it, and some of them are like 2,000 and 3,000 times that you could completely discharge the batteries without causing permanent damage to the, you know, to the batteries themselves. I would really never be in a situation out here where I'm completely discharging the batteries. If it's a sunny day, you know, the batteries will recharge completely after a previous night's observation for within probably 3 to 4 hours. Even if I did not have sun the next day, but it was clear skies at night, I could still run a complete imaging session the following night without worrying that I have enough power in these batteries. Both these batteries, each one's a 50 amp hour. They're wired in parallel, so that gives me 100 amp hours total. And it is more than adequate to power everything that I have running inside here. That includes the laptops, the lights, the mini computers, pretty much all the electronics, the Wi-Fi that's operating 24/7 continuously. So I have yet to have any kind of issues with the capacity that I have now. And if I do need more capacity, I just throw another battery box on here, continue the series in parallel, and it basically just adds more amp hours to the whole setup. So very good, very solid configuration. I've been very happy with it. When the power comes in from the batteries, from the lithium ion batteries that are outside, they actually come into this NEMA box that I have inside. It's attached to the wall. It's just mounted just below a little desk platform that I have here. These power blocks basically distribute power to the different components. So this is our power over Ethernet injector that powers the Wi-Fi access point that's on the outside. It also sends power to these some USB ports that I have, some hubs sitting up on the desk. And also it provides power to these 2 little wireless power management controllers. So I know that there's products out there that, you know, can do very nice, you know, job for powering your telescope equipment. However, I did not want to pay $300 per Pier to have one of those installed. I just didn't need all the functionality that they may be able to offer. What these do basically is, you see they're labeled PC, cam, mount, M&T mount, and heater, and basically there's one for each Pier. So I can control any component on either one of the telescopes wireless through an app on the phone. And I'll show a quick video of that in a second. But, you know, as long as you have internet out here or wireless out here, you know, and you're up at the house, you can turn everything on. You could, you know, turn the dew heaters on, you know, activate the mount, make sure the PCs are fired up. If, say, for example, one of the PCs was acting up, you needed to reboot it, but you couldn't RDP into it. You can just do a remote power shutdown on it and it'll just reset the device. And it works, flawlessly. I haven't had any issues with this at all. In the event that you don't have your phone, say you're out here, you want to get everything started up, but you've left your phone up at the house, there's little switches right here. There's little black switches right there. There's one, they correspond to each one of these little blue blocks. So there's 4 of them there. Just press whichever one you want to turn on, and you can activate it manually too. So you're not, pretty much out of luck if, you left your phone up at the house and you want to power everything up. So this is the app that controls the wireless power switches. You just touch whichever button you're trying to turn on. So like we have the heater, the mount, PC is currently turned on. As you can see, it's highlighted in blue in the camera. I'm just going to turn on, say, the heater. So as soon as I press this, you'll see a little red light right down here turn on. That's going to indicate that the heater was just activated. So tap that. You hear that little click, and then you see the little red light down there. It just turned it on. This can all be done remotely from inside your house. You can even be on the road. It does have a cloud component, so it can be activated, if you're across the country. Now, I will say that these are manufactured in China, so you probably do not want to have these on your main network, just for the fear of, network snooping. So if you have these, I would highly recommend that you put them onto like an IoT network or something that's kind of VLAN'd off from your existing, wireless infrastructure. I mean, it's a great little product, but, in the network world, I trust nobody. And if you want to turn everything on all at once, there's an all on button. And then, of course, to turn everything all off, there's an all off. So if you tap that, it would, shut pretty much everything off. I don't want to do that right now because I have the PC running. So I'll go ahead and tap that. Turn it off. One challenge with operating an off-grid observatory is maintaining a reliable network connection for remote access. To cover the entire property, I've installed several solar-powered network stations around the farm, each with wireless links that form a mesh network. If the primary connection to the observatory ever goes down due to interference, weather, or other equipment issues, the mesh network automatically reroutes the signal through one of the other stations. This redundancy helps ensure that I maintain continuous access to the observatory even during unexpected outages. Other things that I knew I wanted to have in my observatory build just to make life easier when you're out here in the evenings and even at night is one, primarily just a a little workspace. This is a little desk that just kind of folds out, latches out of the way, sits kind of right above where the power distribution is. But in the event I need to spin this larger telescope around, I did not want to have a table that would obstruct the free rotation of it. There is a second monitor on the wall, and that basically connects to the HDMI out on the laptop, so that gives me the ability to run 2 screens, so I can RDP into both telescopes and have one on each screen. Of course, another little shelf up here to hold whatever other components you have, a bat-knob mask, HDMI cables in the event I need to connect to the mini PCs on either one of these telescopes. If they're not responding to RDP, you can still connect to the video, and there's a little wireless keyboard that you can just hook up the Bluetooth connector on and pretty much operate it like it's a standard computer. This little light that I have here, this is an incredibly bright light. I was out here one night and didn't only have my headlamp that had red, and it was kind of frustrating, and I wasn't trying to do astrophotography, so I really didn't need to save the eyes that night. I just needed to see in general. That little thing was a lifesaver. I think it was like maybe $12 on Amazon. Shelving just to hold other components, obviously a toolbox, because you always going to need Allen wrenches and specialty type stuff to work on your gear. In the back, I have these lights. Let's see. Those are basically just 12-volt lights that would go on a truck or a car. They're red in color, so you can turn them on at nighttime and not worry about your eyes not being acclimated for the dark environment. I have an ammeter here that basically shows me what the current power of the battery is, what the current storage state is, as well as the current voltage that's being consumed. So there's one device right now that's 0.1 amp. So, but when I turn this on, normally you'll see it kick up to, sometimes 2 and 3 amps. But, with the battery system we have out there, there's no worry about it running all the way down. A thermometer, humidity indicator, that was always nice to have. And let's see. And of course, the cameras, so you can watch, your equipment at nighttime. always kind of get nervous during the meridian flip. You know, while I haven't had any cables get hung up, the one time that I'm not watching is when it's going to happen. So, you know, that's a wide angle camera, and you can see, you know, the equipment as it's rotating and if any cables are getting hung up. But I always like to just watch when the meridian flip is happening. And this is the laptop that I use to RDP into the mini computers that are on each of the scopes. I have a B-Link mini computer. It's 16 gig of RAM, 512 gig SSD, and the performance is pretty good. I've been very happy with it. I mean, they're by no means a, you know, full-blown workstation, but to run Nina, they get the job done, and I've been very, very pleased with it. I started on the Explorer Scientific 80mm. I started out with an ASI Air because I had bought a ZWO camera, and of course all the ZWO components, and, you know, ASI Air supports, you know, those that particular camera model, and, you know, several of the other components that connect to it. They do not support other vendors' cameras. So on the 127mm, I have an Ogma camera, an Ogma filter wheel. So I needed to find a solution that worked really well. And, you know, Nina checked all the boxes, and I'm actually using Nina on both systems now with the mini PCs, simply because it is truly a powerful little application, a free application. And the B-Links are actually cheaper than the ASI Airs. So had I known all this beforehand, I probably wouldn't have never gone down the ASI Air route and just started out with a B-Link and Nina. But the ASI Air was a fine platform. It's no nonsense. It's very easy to use, especially if you're beginning astrophotography. I'd highly recommend that. Just get you a ZWO camera and a ASI Air. Try to find the equipment used. It's pretty expensive if you're buying at retail, and I'll cover that on my scopes that I have. Neither one of my scopes are brand new. They were both from the used market, but both work very well. The only thing that does not work well on these mini PCs, in my experience, was Stellarium. Stellarium was incredibly graphics intensive and CPU intensive. So the CPUs that are in these are very low voltage CPUs. They're designed for energy efficiency. So they don't have the same powerful cores that you would have on a regular desktop or a workstation model. But, you know, a workaround for that, for not using Stellarium, is the Cardus Lucille application, their Sky Charts application. It works very well with Nina. You basically type in what you're looking for, and let's say we want, say, M51. You'll find it. So right now it's kind of behind the trees here. And this picture, this is basically looking out off my observatory deck. I put pictures in here so I can see the heights of the trees and stuff, and know whenever something's going to pass behind a tree, I'm not going to be able to image it. But in a few hours, M51 will come above the horizon. Basically, in Nina, you would just say get the coordinates from the sky charts, and it'll do your go-to with your telescope. It works incredibly well. So we'll go ahead and close those down, and we'll jump onto the telescopes and what I have currently in my observatory. This first telescope is an Explorer Scientific. It's an 127mm. It's got the FCD 100 glass, which is the premium glass that they sell with this particular model. It has a feather touch focuser, a autofocuser connected to it. We have an off-axis guider right here, and then we have an Ogma 7-position filter wheel with all the astronomic filters, LRGB, SHO, and that's it. And then an Ogma 26 mono camera. I've been very happy with Ogma. The camera takes beautiful pictures, and I think if you are looking for a nice mono camera, definitely check them out. I found that to be about $500 cheaper than the equivalent ZWO brand. And then you'll see that the mount is an EQ6R Pro, incredibly heavy, very, very robust, very sturdy mount. But, you know, it's not one that I wanted to move back and forth to this Pier. Kind of one of the driving factors for ultimately wanting to build an observatory in general. That dew heaters connected here. This is a B-Link mini TC. This is what runs Windows and Nina. That it pretty much runs the entire operation for this telescope. Basically all these wires, this is all connected down to those wireless power controllers. So I'd like to get the wire management a little bit cleaner than what it is right now. But right now there's never any cable snags, so everything's fine with that. Kind of sometimes I shouldn't touch things if they're not broke. This little scope, this is a Explore Scientific 80 millimeter. It's got the standard glass, not the premium glass, but it still takes wonderful pictures. Pretty much has the same, gear on it. It has a dew heater, off-axis guider. This is a one-shot color camera on this one, so the only filter I have in there is an IR cut filter. Again, a B-Link mini PC. This one is mounted on an AN5N mount, which it's a very nice mount. It's a premium mount in my pocketbook, since the cost on it is pretty high, but it's performed very, very well. I would say it's done as well or better than what the EQ6R has done for me. I will mention that Explore Scientific, this isn't an advertisement for them. I just happened to buy this equipment from the same guy on cloudy nights. All my telescopes are used, and the guy's username is JoeInco. JoeInco. So if you're looking for a nice Explore Scientific telescope, definitely look and see what he's got available. I can tell you he's got a lot of sales. He's been very responsive. No issues with any of the equipment that I've bought from him. So definitely give him a look. If you're looking to buy something, an affordable scope at usually about half the price of what it is new. Both telescope piers are made from concrete. I started with 2.5 foot square base reinforced with rebar. It was about 2 feet deep, and then I extended 5 sticks of rebar vertically from that. I waited a week for the base to cure, and then I poured the telescope here using a 5-foot sonotube. For the mounting plate, I used 4 half-inch all-thread bolts that were 18 inches long. I heated the ends with a torch so that I could bend them at an angle. The bending ensures that the bolts cannot turn once the concrete is cured around them. Each pier required 20 80-pound bags of concrete. The top mounting plates have adjustment nuts on either side to ensure you're able to level your equatorial mount. My original pier has been in the ground for a year now, and it looks as good as the day I started using it. I want to take a moment to thank my wife for painting this beautiful mural on the outside wall and door of the observatory. It shows a child standing on an alien moon, looking through a telescope at our galaxy and distant planets in the sky. It perfectly captures that feeling many of us remember. The first time we looked through a telescope and saw the moon's craters, the rings of Saturn, or the faint Andromeda galaxy. That pure sense of wonder. Now, every time I walk into the observatory, I'm reminded of that excitement, and it sets the tone for the night of observing ahead. If you've made it this far, thank you so much for watching. I know this was a long video, but I really wanted to share as much information as I could about the process and what I learned along the way. If I left anything out, or if you have any questions about your own build, feel free to leave a comment below. I'd also love to hear suggestions on how I can improve my current setup. This is still a work in progress, and I'm always learning. If you're watching this video on my YouTube channel, then you can find a link in the description to my Google Drive that contains a spreadsheet that lists the total cost of the various items included in this build. If you're thinking about building something similar, then that might help give you an idea what you can expect budget-wise.